All right. So we are going to be beginning chapter 3 today. But before we do, I'll give a few announcements on sort of what's going on with the quiz and homework and all of that other good stuff. So nothing that I'm going over today will be on the quiz. It will be just all of the stuff we've gone over and things on your homework. For the quiz, I'm going to try to, it's not going to be like, it's going to be doable within, I'd say, about half an hour or so. It's not going to be too bad, I don't believe. If I do change up anything on the quiz, maybe, so I'm thinking later on with the exams, I might make them, out of class that you could take. I'm still thinking about what I want to do with the quizzes. So if you, if there's going to be any changes, you'll hear that in an announcement. Same with, homeworks and all of that other stuff. As well, the homework will be due before class on Monday. So you think of it as like I'm giving you an entire week. So make sure you complete the homework if you haven't. It'll also help you out with the quiz. So with that, I'm going to start chapter 3. And this will be for, a future quiz. But starting chapter 3, it is just motion in 2 and 3 dimensions. We just finished motion in 1 dimension. Let's go with this. So this will be actually kind of like a recap chapter. There's a recap for a bit, and then we're going to get into projectiles. That's sort of the big staple point of this chapter. And we'll do that not today, but in, I believe, next class. Another note on the quiz for Monday, I believe I'm going to just like give 20 minutes of a 20-minute sort of little lecture. I might do like one example problem on chapter 3, what we're doing today. And then I might assign the quiz. Still, you guys should look out for an announcement from me if anything changes. But for right now, we're going over displacement, velocity, and acceleration in 2 and 3 dimensions. So the position vector, this is in 1 dimension, we could just say that's, the x vector, or if it's something moving vertically, it's the y vector. When we are beginning to combine 2 coordinates, we need to start having this position vector r, lowercase r. Position vector r. And this is how we can track something in a 2-dimensional and then a little bit more complex 3-dimensional space. It's a combination of some coordinates. So let's say we have this particle that's just moving on a path. It's either like a ball that's tossed in the air, or maybe it's just something moving along a track. This could be like a roller coaster or something. So we want to start tracking the motion of this particle. And right now it is currently at position X and Y. So these are the coordinates. Let me put in the exact position. So it's a distance X away from the origin. Origin's right here, 0. So it is a distance X. And it is a height. Let's try to make this it is a height of y. That's why it is at position x, y. To write this as a position vector, we're going to say r, it is a vector, is the magnitude x. So this is just the value. And it is in the horizontal direction. That's what we need to, if you haven't seen, I hat, J hat, K hat, I believe I might have skipped unit vectors when we were in the vector section, but this was, I think, a beginning point in a lot of calculus classes is I hat will be the horizontal, J hat is vertical, and K hat is will be sort of the third dimension, whatever we're doing. But in this case, it is magnitude x and the direction, the horizontal direction. So actually, let me put it down here. That is in the I hat direction. Let's make a vector. Try to emphasize, I'm drawing another line in here. There is the vector x I hat. So it's a magnitude x with a direction I hat. Okay. And next up is, for this position vector, is x I hat plus y j hat. So I'm basically just adding two vectors together. Okay, let me more like this. Okay. And this is y j hat, this specific blue vector I just drew. Is a size or magnitude y, and it's in the direction j hat. Adding these two vectors, we've touched this subject before, so that will be this line right here. I won't make it as beefy. Just go like that. That is our position vector r. Oop. X I hat plus y j hat. So we have this way of sort of breaking this position vector. It's sort of tracking where the particle is on this path. We have a way of breaking that up in these nice coordinates. So say it's a little bit of this coordinate and a little bit of that coordinate. You add them together and we're able to find where it is. This being said, there are different frozen. Okay. There are different, let me do this real quick. Good. There we're good. Okay. This follows the same, mindset. There are different position vectors. Position vectors are vector for every single point on this particle's trajectory. For every point. On this particle's trajectory. All right. So say we want to track it over time as it moves along some curve or it moves out in space somewhere in 2 dimensions. So in earlier graphs I've been showing you, I had 1 dimension up here that was distance, and then the horizontal was time. But on this one, we have this new representation. How do we express time passing on this graph? Well, we just have to start labeling things a bit more clearly. Let me pull that up. So this will be like, it'll show you where it moves, and then it'll have to specifically label the time it takes as it moves along. So what I could say about this is, if we want to know the particle's displacement, if we want particles displacement, and that will be the displacement over time, so, or the change in its position, delta R, between 2 points. That's basically, I think we all know by now, that's delta R is just the difference in where it's currently is versus where it was. So final minus initial. In this case, if the particle is going that way, it will be this R2 minus R1. Okay. As for a little picture, we have a way above. You see, we could break each of these position vectors into their components, X and Y. And if we look at comparing 2 points, let's call this, since this is particle at T1, this is the R1. And this one over here, that's pretty good. That one is R2. These are vectors. I should make these arrows. Let's make them an arrow because they are vectors. Okay. So it's the difference in these 2 position vectors. By doing that, we are basically finding this vector. And that is delta R. I'll put it up here. Okay. This is going to be very useful when we want to start doing velocity, which we're going to be doing right up next. Also, this is just kind of like a review, but now we're doing it with a combined 2 coordinates. So think of it as the same steps we've done before, except now we have to do it for X and Y together. All right, so moving on to velocity. Okay, as we've done before, we could take its displacement, however it changes, and find a velocity. So it went this amount of distance, I can time, how long it took to do that. By doing that, we have velocity. Very straightforward. Let's go like that. Okay. So let me like this. Average velocity is just, the two endpoints. Let me make this a bit smaller like that. Okay. Average. The average velocity is just the two endpoints of this displacement. So displacement vector, start and stop, over how long it took to do that. In our previous case, it was just 2 and 1. I'll just keep it general, and I'll say, well, actually, yeah, we'll say 2 and 1 still. It sort of relates to that picture I just drew earlier. With the average velocity, we can also look at the instantaneous velocity. Doing this, I think we might remember what that was. It was the limits of the average velocity. So it was specifically the limits of the average velocity as time went to 0, or time approached. I need to put a t in there first. T approaches 0. And all this is saying, if you're not comfortable with what this is doing, what this is saying, is that this is a derivative of its position over its time. And if you can't quite grasp what that means, is it's just a very tiny sliver of where it is moving towards over how long it takes to move there. So it's just a very tiny little fraction, tiny sliver, sort of a velocity right at that moment. Hopefully we kind of understand this at this point. To calculate this derivative, we're not just going to plug things into here directly. We need to have it a bit more usable. So let me sort of show you what it looks like in something that you might use in a problem. So first off, we need to figure out what dr is. So let's start with the displacement vector. R2 minus R1. And this, so this one is going to be, let's do it out in full before I go to this step. It's going to be x I hat 2 plus y j hat 2, or actually I'm going to put the 2 on the outside. So this is for that second position, minus I hat y j hat 1. You see, now we can combine the terms that have the same coordinate system. So we can combine the I hats together, and we can combine the j hats together. That just gets us Now I have to write the 2 within like this. So x2 minus x1 I hat plus y2 minus y1 j hat. And this 2 minus 1, so x2 minus x1, that's just delta x. Delta x, oop, that should be an I hat, and the y should be y hat, delta y j hat. Actually, let me just put like equal sign. All right. So we have this representation that's the position vector r equals the displacement of the x in the x direction and the value y in the y direction. So now let's plug that into this up here for velocity. Velocity equals, yeah, let's limits as time approaches 0, delta r, delta t, and then putting it in, putting the full term in, we have the limit of delta t approaching 0 is delta x I hat plus delta y j hat over, all of it is over delta t. And maybe you can see where this is going. I could split this up into 2 separate limits. Limit as time approaches 0, delta x over delta t I hat plus the limits as time approaches 0, delta y over delta t j hat. And we've getting real close to what we might see. Previously, when we've done velocity, I did it for, all x's. So maybe we've seen this term before. The limit of delta x over delta t, that is just v of x. It goes, the reason that this term right here is v of y. So the instantaneous velocity in the x direction, the instantaneous velocity in the y direction. So we have this term. Let me just do it all in full so you guys have it all. And I might have to shrink this a bit. We move to the next paragraph. We have the velocity is equal to the x derivative, xt, in the horizontal direction, plus dy dt in the vertical direction. And as I've sort of pointed out up here, that means that, let me emphasize this. So that means the velocity, instantaneous velocity on, a 2-dimensional grid. And now you can see I don't have any sub values right here, is equal to its component pieces. So it's equal to the velocity specifically in the x direction, horizontal direction, plus the velocity specifically in the vertical direction. So we have, the total velocity is made of its two separate parts added together. So this is kind of a useful thing to remember, maybe highlight. I'm probably going to have to shrink this. Let's see. Now we have formula for velocity in 2 dimensions. Oh yeah. Let me shrink this work a bit. I'll make this, legible on the notes when I put them up later. Oh, perfect. So we have this way to find velocity. It's made of its component pieces. Maybe we don't want, if we have an answer, in this form, it'll say velocity equals something I hat plus something j hat. And you got to keep those two terms separate. Maybe I don't want to figure out, horizontal velocities and vertical velocities. I just want a total magnitude, a total velocity. So right here, magnitude. And I don't quite want this result. So to find magnitude of something, it is just going to be using Pythagorean theorem. So V, the magnitude, and I'm not putting a vector sign like that because this is just a number. Vx squared plus Vy squared. And there'll be, just a number of a given speed of, the hypotenuse of the triangle. Finding the angle, there's, problem asking you a specific direction that it wants you to solve for. Again, use inverse tangent. I think one of my notes, I went over why we're doing this, but we have, make it a bit clear, we have the y component on top, x component on bottom. So if you're unclear on this, I'd say check out some previous notes. Finally, I have a little graph picture thing. I don't know if, what time is it? Yeah, we'll do one little section. Let's find, I'm trying to keep it the same size. There we go. Like that, perfect. Let's find the velocity of this segment right here. What is the velocity of this? So I've added times to these points. I've also clarified the coordinates. So this is at position 1, 4, position 5, 3. And let's just call this, path A or vector A, or you could call it displacement vector A, whatever you want to call it. We want to find velocity of that. Actually, yeah, let's call that displacement vector A. Okay, so we want to find velocity A of this, segment. Trying to make that look like a capital A. There we go. We want to find this. I'll just put it in sort of like right. Yeah, I'll put it right there. Well, we know that it's going to be made of its components. So velocity A of that segment is going to be made of velocity A, specifically the X component. You know, what's the velocity of it moving in the X component, horizontal component. We're going to have to add that to its velocity of that segment in the vertical direction. And we know from above, you know, just above this line, the top of the screen, we know that Vx, oh, there we go. Vx is just delta x over delta t, the change in horizontal distance over the change in time. The velocity in the y direction is just the change in vertical distance over the change in time. I have to put a vector right there. Okay. So this is actually much more simple than it seemed. So we have velocity A. I'm just going to put them all in one big equation for right now. Velocity A is 5 meters. And I think I forgot to put a unit on this. So I'm going to say these are meters up here and meters down here. So that way I don't have to put meters on all of these numbers. So we'll say 5 meters. You know, what's it moving in the X direction, in the horizontal direction? It's going from 5, that's its final place. So final minus initial. How long did it take? So final is 2 seconds minus initial, 0 seconds. And that is the X horizontal velocity right here. You're going to have to add the vertical velocity. Okay, so final is 3. Let me get rid of that. Okay, 3 meters minus 4 meters. And how long did it take? It took the same amount of time because this is final and initial. 2 seconds minus 0 seconds. And this is the J component. Summarize this. It is just 4 meters over 2 seconds. I hat direction. This is minus minus that's going to be 1 over 2. Let me make it 1 meter over 2 seconds. In the J hat direction. Realize this is going to be much too big for fitting in stuff. The rest of this little section, so I'm going to shrink it a bit. Right there. All right. We have this new, well, we technically have the answer. We have velocity of this segment is 2 meters per second in the I hat direction and minus 0.5 meters per second in the J hat direction. This is kind of what I was talking about earlier. maybe, it's hard to tell how fast this is actually moving. It's moving, I understand it's moving 2 meters per second this way and minus half a meter per second that way. But what if I want to combine them? I find the magnitude. Let's do, oh, I'll put it right here for right now. Okay, so the magnitude of these two. So this is Vx, this is Vy. Let's square Vx, so that's going to be 4 meters squared per second squared. Now let's square the y component. So it's adding 0.25 meters squared per second squared. Adding those up and then taking the square root, we have an answer of the magnitude of this velocity is about 2.06 meters per second. Okay. So that is, a bit more clear for me to understand that this line segment right here is just a little bit above 2 meters per second. And this minus sign right here, that was purely just to show that it's, going downward. It's going downward like that. Okay, so there's a result and there's a result. Let's move on to, relative velocity. Okay. Relative velocity. Sometimes when we're doing we're finding a velocity for something, we need to be clear about not just, where the thing's moving. We need to be clear about the reference frame around the thing that is moving. So think of it like, have you guys ever sort of no, it's well, maybe you've seen it. I should have pulled up a video beforehand. If you're in an elevator and or some sort of room that is falling, falling down, and you're looking around, things might just seem to float. So your relative perception is within the elevator. You can't perceive the bigger reference frame around it. So this is kind of what I'm talking about with reference frame. You have, in that example, you have a very small reference frame, the elevator. Let me maybe move on to another example. Well, we'll get to the example at the bottom. Okay. So a reference frame is just a collection of points around the thing you're measuring. So if I am in a car, or let's make it a school bus, and I'm in the back of the school bus. The school bus is moving along the freeway, and then I start just from the back seat, start walking forward. To me, I am just moving forward, just a little bit, a meter per second or so. But we have to add the bigger reference frame on top of it. So not just me moving 1 meter per second, it's me with that 1 meter per second, then added to however fast the bus is moving. So we can consider the motion of the reference frame with respect to this larger reference frame that's around it. Usually we think of things as this larger reference frame as the outside world, everything's is at rest, or we might say the ground is at rest, is the big reference frame. So we have to just consider these things. This is just kind of like a wordy example. There's a few examples in the book. I'm just kind of summarizing a bit here. Let's see. Right, so right, so we can connect a reference frame to the coordinate system to make measurements, but then we need to compare it to a larger reference frame. And there we go. Now, here's this example that at first I didn't quite like because there were a lot of little abbreviations that made it a bit unclear to understand, but maybe I can help you guys out with this. So after a while, I did begin to like this example. We have this particle, or you think of it as like a ball or something, and it's going to be moving with a reference frame. So particle P, and it's moving in its own little, reference frame, its own box. We're calling that A, reference frame A. Okay, but reference frame A, this box, is also moving inside of its own bigger reference frame that we're going to call B, reference frame B. So to think of how is the particle moving with respect to that larger reference frame. In that case, the particle with respect to that larger reference frame B, that big, think of it as you have this ball moving inside of a box, reference frame A, but then the box itself, reference frame, is moving, outside. So how fast is the ball or the particle moving, in total? That is going to be adding these two velocities together. So it's however fast the particle was moving in that reference frame, A, and we're going to add how fast reference frame A was moving in the larger reference frame B. You see, it's a bit dicey trying to understand these indices. This is where maybe this example that I will draw will help. We have this, flat top train car, and it's going to be moving on some train tracks. We have this ball that we're going to roll on top of it. So we have a ball right here. and we're going to roll the ball that way. Now, if I'm sitting on the train car and I'm rolling the ball, it just looks like it has this velocity right here. Remember, the size of the vector is also important. So it's to scale. So it has this velocity. Now try to keep the indices the same as this example, maybe make it make sense. So a ball is rolled. Let me put right here particle. Particle P, just to clarify for ball, across a train car. So it's going to be going this way with a velocity of train car itself is moving on the train tracks. It's going that way. The train car is also moving with respect to the ground. So the ground itself is a bigger reference frame. So the ground I'm going to put is G. So the train car is moving with this velocity. Let me make more room. The car is moving with respect to the ground. Okay, so let's add these two vectors together. And we are going to figure out how fast is the ball moving to someone standing out here. Someone standing, out on here on the ground, looking at the ball on this bigger reference frame. So we have to add these two vectors together. The person out here on the ground will see this velocity. Velocity of the particle or the ball P with respect to the ground. And that's just adding these two vectors. With this is in this reference frame. The ball is in the train car reference frame. And the train car is moving with respect to the ground, CG. What does this look like, graphically with just adding the vectors? I would put like, see if I could match that. It'll look like that. That's roughly the same size as that. And I'm going to add this head to tail method right about there. Okay, so I'm adding these two vectors that will give me this new vector like this, all the way out to that point. There we go. So this large line right here, that is velocity of the ball with respect to the ground, which is these two added together. So this vector right here, this velocity, is what someone on the ground would see. Okay, so try to maybe make that a bit clearer. If you're to take a look in the book, Took me a while to sort of digest that. Maybe it will make more sense to you if you were to look that over. All right, the next section is, oh, okay, I'll do a little example on some relative velocity. So this will be, I put this in here because maybe it would help with figuring some things out. So we have an, let's put the problem in. A pilot wishes to fly a plane due north, so directly north, relative to the ground. So he's maybe in one city, he wants to go directly up to another city. Directly north to another city. The airspeed of the plane is 200 kilometers per hour. And the wind is blowing from west to east at 90 kilometers per hour. Okay, in which direction should the plane head? Okay, so the plane wants to fly due north, so directly north. Let's put a little compass. All right, so the plane wants to go directly north, like that. Relative to the ground. So that's a velocity. And think of it as the velocity of the plane with respect to the ground. Okay, so velocity. The airspeed of the plane is 200 kilometers per hour. We'll get to that in a minute. And the wind is blowing from west to east at 90 kilometers per hour. So it's going from west to east, like that. That is the velocity of, we'll say, air. Actually, let's put like W for wind. The wind with respect to the ground. So these are the two things that we know. We want to know, we want to work out which direction should the plane sort of aim in order to end up going this direction. So I can add these two sort of slices together. So if I put the, let's see, go like this. How do I want to do this? If we put the vector like this, come on, like that, that means that if the plane directly, oh, I know what to do. Okay. If the plane directly took off going north, then it will be affected by the wind and it will be turned that way. So it has to sort of compensate for the wind. It has to steer into the wind. And that's why I'm going to position this vector right here like that. So that means that the plane starts right here, has to aim this way, let me connect it like that. The plane has to aim that way because of the wind moving past. So the velocity of the plane with respect to the wind. So I'm going to say W. So if the plane takes off this way, this is just sort of clarification. If a plane takes off going this way, the wind will constantly be affecting it, and ultimately it will end up going that way by adding the two vectors together. All right. So this is just showing that the velocity of the plane with respect to the ground is actually the velocity of the plane with respect to the air wind plus the velocity of the plane, the wind with respect to the ground. I wish I prepared a picture of like some wind blowing. Sort of like an intuitive problem that's hard to explain. Okay. So we have this sort of formula for these vectors. Let's find out what the angle is. So in which direction should the plane fly? So it has to go this way. Velocity, oh, and there should be a velocity, there should be an arrow on top of these. So it has to go at some angle. It has to go at this specific direction. So we need to know that angle. Since these two things right here are perpendicular, we can use some trigonometry. That is the velocity of the wind with respect to the ground over the velocity of the plane with respect to the wind. So we could just plug in the values that we have been given. Kilometers per hour over 200 kilometers per hour. And a lot of this cancels, even the units cancel. So we have just 9 over 20. So we can rewrite this as theta is the inverse sine of 9 over 20, which is 27 degrees. And the wording on this, since we are doing with actual like cardinal directions, we could say 27 degrees. And you see, I'm like, we're heading west. So I'll say west of north. All right. What is the ground speed? So what is someone on that larger reference frame? What are they seeing? What is the value of this vector? I'm sorry. What is not this vector, it's this vector. So what is the ground speed of the plane? So this is where we can use Pythagorean theorem that says velocity of the plane with respect to the wind squared is, since this is a right triangle right here, is velocity of the wind with respect to the ground squared. This is basically just c squared equals a squared plus b squared. Velocity of plane with respect to the ground squared. Does all have vectors? Okay. All right, so we're going to rearrange this because we want to find this one by itself. Actually, at this point, I could just leave them off because this is going to be a magnitude. Equals, I'll just skip a couple steps. Not a, it's wind squared. All right. 200 kilometers per hour squared plus minus 90 kilometers per hour squared. It's going to equal 180 kilometers per hour. So that's what someone on the ground is going to see this airplane fly overhead as. That's going to be this vector right here. Even though the plane is flying in this direction at 200 kilometers per hour, the wind right here is counteracting it and making it fly this path right here. So this is sort of the conceptual bubble I was trying to craft for relative velocities. And the last little bit I want to go over today is just acceleration vectors. It is, pretty much the same as we've done before. So let's pull that up. Acceleration vectors. I'll just highlight these two already. So we can find the average acceleration, and where there's an average acceleration, we can find the instantaneous acceleration. This is the same thing we've done before. So if you have average acceleration, this is going to be in multiple dimensions. So I'll just have it as A average is equal to the change in velocity over the change in time. Where there's an average velocity, where there's an average acceleration, there's a instantaneous acceleration. So what is the acceleration at a given specific moment? So limit as we take a very small sliver of time. and just fill this out pretty quick. And that's pretty much a derivative of the velocity. If you were to look at a graph, that would be the slope on a velocity versus time graph. Now, to calculate the instantaneous acceleration, you can break it up into its component parts, like we've done before with the velocity. So okay. So we have this acceleration is, well, actually, no, I started before. Now with the acceleration, first we need to figure out what velocity is. We just went over this a couple minutes ago. It is, velocity is made of its own component bits. This j hat for the vertical. And we're going to do a third, just so I could demonstrate for 3 dimensions. That is going to be, well, if, we have horizontal and vertical, think of the third axis as coming out of the page or coming out of your screen. So I'm going to rewrite this in its derivative form over here, or as you'd see it for position. Dx dt I hat plus dy dt j hat plus d z dt k hat. Now that we have these sort of bits for this, let's plug them in. I'm not going to do like the limit and all of that again. I'm just going to go right to this step. So the acceleration is the derivative of the x velocity with respect to time. This is in the horizontal direction. It's the derivative of the vertical velocity in the vertical direction. Add z over t in the, I guess you call it like height dimension. It's like length, width, and height. So we'll say height for that one. I don't need a vector arrow on top of these because I have these component directions out here. So that just popped in my head. I figured I'd just mention it. And if I was to rewrite this in terms of position, we would have second derivative in terms of x in the I hat direction, second derivative of y in terms of t squared. There should be a squared on the bottom. J hat plus the second derivative of z over dt squared, the k hat direction. All of this to get to, we have the acceleration term is just made of its own components. AX in the horizontal, AY in the vertical, and AZ in, we'll say, the height out of the page. All right. And do we have time? Let's try. This is all I want to get through and we're good. Okay, we have, what do I have? I'll put that out also. So of a thrown baseball is given by this function. Find its velocity and acceleration as a function of time. So you see this is a bit odd sort of writing of a position because there is this velocity multiplied by t for time. There's one here and there's t squared in that term right there. So let's find these values. Let's split it up into its components. There's only a horizontal I hat and there's only a vertical component. So let's say x equals, let me make it higher, x equals, well, what is this sort of horizontal position? Just the position by itself. Well, that is just this term, 1.5 meters plus 12 meters per second times t. And what is the y position? That is just this term, just the whole thing. So it'll be 16 meters per second t minus 4.9 meters per second squared times t squared. All right, what is the velocity? In terms of t. So let's take a derivative of this component or this, term with terms in terms of t. So that goes to 0. The only thing that's left is this 12. If we take a derivative with respect to t, that will just be 12 meters per second. So let's do the same thing. I'm going to take a derivative of y. Sixteen meters per second minus 2 times 4.9 meters per second squared t. All right. Next bit, acceleration for the x term. Well, that's just the derivative of the velocity in terms of x. Acceleration in the y term is derivative vy dt equals, so there's no t in this term. So that is 0 minus, there's only 1, so it's going to be 2 times 4.9. That's 9.8 meters per second squared. All right, so we have our velocity and our acceleration. So the velocity will be 12 meters per second in the horizontal direction plus 16 meters per second minus 9.8 meters per second squared times t in the vertical direction. And the acceleration term is, let's make these better arrows. Acceleration term is just negative 9.8 meters per second squared in the vertical direction. That is our result. Hopefully that will clear things up on what we're supposed to be doing and when and where we're going to be using the derivatives. It's mainly when we have a function given like this. Other than that, make sure you guys finish up your homework and turn it in before class on Monday. It'll be very helpful on studying for the quiz. I'll try to keep it in roughly the same vein as the homework. And yeah, if you guys have any questions, just let me know. Other than that, I'll see you later.